The most obvious problem, distance. Now, how far away is the nearest star to us? Well, it's called Proxima Centauri, and it's about 4¼ light years away. What does that mean? It means that light, which travels faster than anything we know of, takes 4¼ years just to get from that star to us. 4 years, and that's the nearest one. Most of the stars you see at night are much, much farther away. Some are hundreds of light years away. The star Sirius, one of the brightest ones we see, is about 8½ light years away. Now you might say, well, okay, it's far, but we've gone to the moon, we've gone to Mars, eventually we'll work up to going to another star. And I understand that thinking, but I want to explain to you why this is not just a bigger version of the same problem. It's fundamentally different. You see, when we think about traveling in our solar system, going to Mars or even to Jupiter, we're dealing with distances that, while large, are comprehensible to us. The time scales are long, yes, but they're measured in months or a few years. But when you get to interstellar distances, you're talking about time scales that are measured in decades, centuries, or longer, much longer. And that creates problems that are not just engineering problems, they're physics problems. The biggest one, the one that really stops you if you think about it clearly, is the speed of light. Einstein showed us, and this has been confirmed countless times in experiments, that nothing can go faster than light. Not faster, period. This isn't because our rocket engines aren't powerful enough. It's not because we haven't invented the right technology yet. It's because of the fundamental structure of space and time itself. There's something deep about the universe that prevents this. And you can't get around it by thinking harder or building bigger machines. So if light takes 4 years to get to Proxima Centauri, the minimum time it would take a spaceship to get there is also 4 years. That's if we could travel at the speed of light, which we can't. We'd have to go slower, much slower. Now you might ask, and this is a good question, why can't we just go really, really fast? Why can't we reach 90% the speed of light or 95%? And the answer is energy, enormous amounts of energy. Let me explain this to you. Imagine you're in a spaceship and you want to accelerate to some speed. Let's say you want to reach 10% the speed of light. That's about 30,000 kilometers per second. Now to get something to that speed, you need to impart kinetic energy to it. The faster you want to go, the more energy you need. And as you get closer to the speed of light, the energy requirement goes up exponentially. It doesn't increase linearly. It gets worse and worse the faster you try to go. The equation that describes this comes from relativity, and it tells us that as you approach the speed of light, you need more and more energy to push you faster. By the time you're at 90% the speed of light, you need an enormous amount of energy. At 95%, it's even more enormous. At 99%, the energy requirement becomes almost unimaginably large. Let me give you some concrete numbers so you can understand what I'm talking about. If you wanted to accelerate a spaceship with just 1 ton of mass, 1 ton, which is tiny compared to a real spaceship, to 10% the speed of light, you would need an amount of energy equivalent to the energy released by several megatons of TNT. Several megatons. And that's just for 1 ton, and that's just for 10% of light speed. If you wanted to reach 50% light speed with a spaceship that weighs, say, 1,000 tons, you'd need energy equivalent to millions of megatons of TNT. Where would that energy come from? Well, some people have proposed antimatter propulsion. When antimatter comes into contact with regular matter, they annihilate each other and convert into pure energy. Einstein's E equals mc squared. And this is, in theory, the most efficient energy source possible. If you could produce antimatter and store it safely, it would give you the most energy per unit of mass of anything we know. But here's the problem with that. We can't produce antimatter in any significant quantities. We can make a few atoms of it in particle accelerators, but the amount we're talking about, the amount you'd need to power an interstellar spaceship, is completely beyond our current capability. And I mean completely. We're not talking about something we'll be able to do in 50 years. We might be able to do it someday, but we have no idea how. It's not just an engineering problem. There are fundamental physics issues about how you'd even store that much antimatter safely. And even if you could produce it somehow, let's say in the distant future, there's another issue. Not all the energy from the antimatter annihilation goes into propulsion. A lot of it gets lost as radiation, as particles that fly off in different directions, as heat. So your efficiency is not nearly as good as the theoretical maximum. Now, there's another fundamental problem I want to talk about, and this one is really important. It's what happens when you travel at very high speeds through space. Space, you see, is not empty. We imagine it that way. We think of interstellar space as this perfect vacuum, like a theater that's been cleaned and swept with nothing in it. But that's not true. Interstellar space contains gas. There are atoms of hydrogen, helium, and other elements scattered throughout. There's also dust, tiny particles of matter, and there are cosmic rays, high-energy particles coming from all over the universe. Now, when you're traveling slowly, these things don't matter much. The occasional atom here or there doesn't do anything to your spaceship, but when you're traveling at a significant fraction of the speed of light, let's say 30% or more, something very strange and very dangerous happens. From the point of view of the spaceship, it's not the spaceship that's moving, it's the universe that's moving toward it. And because of relativity, when particles hit you at relativistic speeds, speeds that are a significant fraction of light speed, they have enormous kinetic energy. Remember what I said about energy requirements? Well, the same thing applies here, but in reverse. A hydrogen atom hitting you at 50%, the speed of light has more kinetic energy than you'd expect from classical physics. It's incredibly energetic. It becomes effectively hard radiation, ionizing radiation. What this means is that as your spaceship plows through the interstellar medium, it's being bombarded by this relativistic wind of particles. These particles are hitting your ship with tremendous force and energy. They're ripping electrons off atoms, creating ions. If there's an unshielded person in that spaceship, they would receive a lethal radiation dose, not in minutes, in seconds, and there's more. There are also dust grains out there, tiny little specks of solid matter. When these hit a spaceship traveling at 30, 40, or 50% the speed of light, the impact is like being hit by a bullet. A tiny speck becomes a projectile with enormous kinetic energy. It could punch through the hull of your spaceship. Now, you can protect yourself from this. You can put shields in front of the spaceship. But shields have mass, and if you're trying to reach high speeds, mass is your enemy. You have to carry all that mass with you, and carrying mass requires energy. It's a trade-off. You can shield yourself, but it costs you a lot in terms of the energy and resources you need to accelerate. And here's something else that's interesting. As you go faster and faster, approaching the speed of light, something happens to your perception of the universe. The light from the universe gets bunched up in front of you. It's called the beaming effect, related to something called relativistic aberration. At very high speeds, nearly all the visible light from the universe, the stars, everything, gets concentrated in a narrow cone in front of you. You're essentially looking out at the universe through a narrow tunnel. The universe becomes like a bright point ahead and darkness to the sides and behind. It's a strange effect, but it's real. Now let me talk about something else that people sometimes bring up, and I want to address it because it shows a misunderstanding about how physics works. People sometimes say, well, what about time dilation? And they think this might be a way around the speed of light problem. Time dilation is real. Einstein showed us that if you travel at very high speeds, time passes more slowly for you compared to someone who's stationary. If you traveled at 95% the speed of light to Proxima Centauri, which is 4 light years away, you might only experience a few years passing while decades pass on Earth. That's genuinely true, and it's a consequence of relativity. But here's the key point. Time dilation doesn't help you go faster. It doesn't let you circumvent the speed of light limit. What it does is it changes your personal experience of the journey. From Earth's perspective, you're still taking more than 4 years to get there because you're traveling slower than light. You're just experiencing less time personally. So if you left Earth in the year 2050 and traveled at 95% light speed to Proxima Centauri, you might experience only 4 or 5 years of subjective time. But when you arrive, Earth time might be in the year 2100 or beyond. Everyone you knew on Earth is older or dead. The world has changed. So time dilation is an interesting effect, but it's not a solution to the distance problem. It's just a weird consequence of traveling at relativistic speeds. Now, some people have heard about things like wormholes, or they've read about concepts like warp drives, and they think maybe these could be used for interstellar travel. They imagine some kind of shortcut through space-time, or a way to manipulate space itself to create a bubble that can travel faster than light. And I want to be very careful here because I don't want to say this is impossible in a way that sounds closed-minded. Science should be open to possibilities. But I want to explain what the actual situation is with these ideas. According to Einstein's general relativity, wormholes, which are sometimes called Einstein-Rosen bridges, are theoretically possible. They're solutions to the equations of general relativity. They would be like tunnels through space-time that connect two distant points. If they existed and if you could use them, you could theoretically travel vast distances through space instantaneously or nearly so. But there are several enormous problems. First, we don't know if wormholes actually exist in the real universe. Second, Even if they do exist, we have no idea how to find one or how to use it. Third, and this is crucial, theoretical analysis suggests that any wormhole would be unstable. It would collapse almost immediately. If you tried to go through it, it would close up before you could make it to the other side. It would be like trying to jump through a door that's slamming shut. And fourth, there's an energy problem. The theoretical calculations suggest that creating or stabilizing a wormhole would require access to exotic matter with negative energy and in quantities that are just staggeringly large. We're talking about energies on the order of what's called the Planck energy, and that's a quadrillion times larger than the most powerful particle accelerator we have on Earth. So wormholes, as fascinating as they are theoretically, don't offer a practical solution to interstellar travel. What about warp drives? You know, the idea of somehow warping space-time around a spacecraft so that it could move faster than light. Well, this is an even more speculative idea. There are some solutions to the equations of general relativity that seem to describe something like this. The most famous one is called the Alcubierre metric, but the problems are even more severe than with wormholes. You'd need exotic matter, you'd need enormous amounts of energy, and frankly, we don't even know if the concept is physically realizable. It might be that general relativity permits these solutions mathematically, but nature doesn't actually allow them. And here's something important. Even if a warp drive were somehow possible, it would violate causality. It would allow time travel, which brings in all sorts of paradoxes and problems. The universe seems to have built-in protections against this. Nature doesn't allow the kinds of things that would create logical contradictions. Now you might say, well, okay, maybe we can't do faster than light travel, but what if we just accept that interstellar travel will take a long time? What if we build generation ships? Big spaceship where people live their whole lives and their descendants eventually reach another star. This is sometimes called a world ship, and this is actually the most plausible way to do interstellar travel within the constraints of known physics. You build a huge spacecraft. It's self-sustaining like a little world, and over centuries or millennia, it slowly makes its way to another star system. When it gets there, the descendants of the original crew finally arrive. But even this has enormous problems. For one thing, building a spacecraft that's large enough to support a human population for hundreds or thousands of years is a staggering engineering challenge. We've never built anything like that. We don't know how to do it. It would need to be self-sustaining for water, air, food, all resources. And it would need to maintain the integrity of the structure for centuries in the harsh environment of space. That's not an easy problem. But there's a deeper problem. It's a psychological and sociological problem. You're asking people to spend their entire lives on a ship. Their children will grow up on a ship. Their grandchildren will grow up on a ship. Everyone they know and everyone they will ever know will live and die on that ship. After dozens of generations, would the people on that ship still be motivated to reach a distant star that none of them will ever see? Or would they ask, why are we doing this? Why don't we just stop somewhere? Why do we have to reach this particular star? These are not trivial questions. They get at fundamental human psychology. And there's another issue. We'd need to be very careful about genetic diversity. If you're taking a population of humans on a spaceship, that population has to be large enough to maintain genetic diversity. Too small a population, and you run into problems with inbreeding and genetic diseases, you'd probably need thousands of people, and you'd need to maintain the genetic diversity carefully. How do you manage that psychologically? Do you control reproduction? That sounds dystopian. These are real hard problems. Another approach people sometimes talk about is hibernation or suspended animation. You put the crew into some kind of sleep, and they wake up when they reach their destination. This is more science fiction than reality right now. But let's think about what it would require. First, you'd need a way to preserve a human body in a state where it can be revived without damage. We can't do this now. We barely know how to do it for small animals. The ice crystals that form when you freeze tissue damage the cells. We'd need to develop some kind of cryoprotectant that prevents this damage. And then we'd need a way to revive the person without further damage. This is not just a technological problem. There might be fundamental biological problems that make it very difficult or impossible. But let's say we solve that somehow. There's still the problem of the journey itself. If your crew is asleep, then the spacecraft has to be completely autonomous. It has to navigate, make course corrections, respond to emergencies, all without human intervention. For decades or centuries, the reliability requirements are just enormous. And what if something goes wrong? What if the ship develops a problem and there's no one awake to fix it? There's also a legal and ethical question. If you put someone into suspended animation, are you responsible for what happens to them? What if the revival doesn't work? What if they wake up in a different world with different values and ethics than when they went to sleep? There are deep questions here. Now, I want to talk about something that I think is important, and it connects to why I find these kinds of discussions so interesting. I want to talk about the difference between what's theoretically possible and what's practically feasible. You see, there's a tendency in discussions about future technology, what I might call cargo cult thinking about science, where people say, well, Einstein's equations allow for wormholes, so wormholes must be possible. Therefore, interstellar travel via wormholes is possible. But this is not how physics works. Just because an equation allows for something doesn't mean it actually exists in nature, and it certainly doesn't mean we can use it. Let me give you an example. The equations of general relativity allow for solutions that describe closed time-like curves. That sounds like time travel. You can write down the equations, plug in some numbers, and get a solution that looks like it permits time travel. But does that mean time travel is actually possible? We don't know, but there are very good reasons to think it isn't. Nature seems to have built-in protections, what physicists call the chronology protection conjecture. That prevents paradoxes. So even though the equations allow it, nature doesn't permit it. It's the same with faster-than-light travel. Yes, you can write down solutions to Einstein's equations that seem to allow it. But does that mean it's actually possible? The evidence from actual observations and experiments suggests no. Every time physicists have looked carefully at whether these solutions could actually be used for faster-than-light travel, they've found fundamental problems. There are always reasons why it wouldn't work. And here's something else that's important. Being open to new ideas doesn't mean believing in every speculative idea. Being scientifically honest means saying, here's what we know, here's what we don't know, here's what we've tried and found doesn't work, and here are the constraints that nature seems to impose. It means not fooling yourself. I think what we need to do is accept the hard truth about interstellar travel. The hard truth is that it's limited by the speed of light. Any spacecraft we build will take many years to reach even the nearest stars. That's not going to change. And I think that's worth accepting because it changes how we think about the problem. If you accept that interstellar travel will necessarily take a long time, then the approaches that make sense are the slow approaches. You build efficient spacecraft that can sustain human life for decades. You think carefully about the biological and psychological challenges. You plan for multi-generational journeys. These are hard problems, but they're not impossible problems. They're problems that humans might be able to solve, given enough time and resources. But if you keep hoping that some breakthrough will let you exceed the speed of light or that some exotic physics will come along and change everything, then you're fooling yourself. You're building your plans on sand. Now, someone might ask me, but aren't there new developments in physics? Aren't there things we don't understand yet? How can you be so sure? And that's a fair question. Science is always open to new discoveries. But here's the thing. I'm not saying that because I'm attached to current physics. I'm saying it because of the evidence. Special relativity has been tested thousands of times. It's been tested in particle accelerators, in cosmic ray observations, in atomic physics, in nuclear physics. Every single test has confirmed it. The speed of light limit is one of the most firmly established facts we have in physics. Could there be some completely new physics that changes everything? Well, sure, there could be. But you can't plan for that. You can't base your understanding of the world on the idea that all the evidence is wrong and there's some secret truth that nobody has discovered yet. That's not science. That's fantasy. So let me try to summarize what I've been saying. Interstellar travel is incredibly appealing as an idea. We see the stars. We want to go visit them. But there are fundamental laws of physics that constrain what's possible. Nothing can exceed the speed of light. Getting to relativistic speeds requires enormous amounts of energy. The interstellar medium itself is hostile to high-speed travel, and we have no realistic way to circumvent these limits. That doesn't mean interstellar travel is impossible. It means it's limited. It means it's slow. It means it requires solving enormous engineering problems and enormous biological and psychological problems. But you know what? If humanity were ever to achieve interstellar travel, if we really did send a spacecraft to another star, I think it would be one of the greatest achievements in human history. Not because of the technology involved, though that would be impressive, but because it would represent our willingness to think long-term, to plan for centuries or millennia, to work on something that we ourselves might never see the completion of. That's a kind of thinking that we don't do very much. We're usually focused on short-term problems and short-term gains, but interstellar travel would require a different kind of vision. It would require saying, yes, this is hard, yes, it will take a very long time, but it's worth doing. And I find that kind of thinking very appealing. I think that's something to aspire to, even if the physical constraints mean that it's always going to be very difficult and very slow. So the verdict, as I see it, is this: interstellar travel will happen eventually, maybe, probably, but it will happen very differently than we imagine. It will be slow. It will take a long time, and we'll have to be very clever and very dedicated to make it work. And that's actually more interesting to me than the fantasy versions where we imagine fleets of ships traveling faster than light, exploring dozens of star systems. Because the real version, the version that's constrained by actual physics, that's a much harder problem, and harder problems are more interesting. Thank you.